In every single production system we build, there are these silent ticking time bombs. And they're not bugs in our code. Not really. There's something way more insidious. They're things that are designed to expire. I'm talking about secrets, credentials, tokens, certificates. They all have a shelf life. And when they hit it, they take our services down with them. So today, we're going to learn how to defuse these bombs.
All right, so here's how we're going to tackle this. First, we'll dig into the most common way this all goes wrong, the 24-hour time bomb of rotating credentials. Then we'll look at some really solid fixes for it, and after that, and this is the cool part, we'll see how this exact same problem pops up again with TLS certificates, how trust itself can expire, and of course, what we can do about it.
So this is where it all begins. A service starts up, it reads its configuration from the environment, it connects to a database. Seems simple enough, right? But what's really happening is that a critical failure is already in motion. The clock has started ticking.
Just think about it for a second. Chances are your service is running on credentials that are absolutely guaranteed to fail. It's not a question of if it's going to happen, it's just a question of when.
Let's just walk through a classic 3 a.m. outage scenario. Your service deploys, reads its database password from an environment variable, and everything looks great. It works perfectly for about 23.5 hours. Then, right on schedule, your secrets manager, let's say it's Vault, does its job. It rotates the password. The problem is your pod has no idea this happened. It's still holding on to that old, stale password. So new connection attempts start failing. And pretty soon your entire connection pool is dead. You've got a total outage.
And here's what makes this so incredibly frustrating to debug in the middle of the night. The service doesn't just crash. It's more like a slow bleed. See, the existing, already authenticated connections in your pool, they keep working just fine. But as they get used and recycled, they're replaced by new connection attempts, which fail. This slow degradation sends your on-call engineer on a total wild goose chase, looking at all the wrong things.
And this is the real trap, right? You're seeing authentication failed in the logs, sure, but you're also seeing rising latency and connection timeouts. So you think, is the database overloaded? Is there a weird network issue? The on-call engineer even checks the pod's environment variables, and the password looks totally correct because it is the password that was set when the pod started. The real root cause, that rotated credential sitting in Vault, is often the very last place anyone thinks to look.
Okay, so now that we're all feeling the pain of that 3 a.m. page, let's talk about solutions, because there are really robust, well-established patterns to prevent this entire class of failures from ever happening.
So it all comes down to this one crucial thing. We have to change how our applications get their secrets. Environment variables are static. They are frozen in time the moment a container starts up. That makes them fundamentally incompatible with anything that rotates. The solution? Use file mounts. They're dynamic. When a Kubernetes secret gets updated, the file that's mounted into your pod gets updated on the file system, and that gives our app a way to actually see the change.
And yeah, this picture just says it all, doesn't it? On the left, the environment variable is a snapshot, a picture taken at one moment in time. But on the right, the file mount is like a live video feed, a window into the current value of that secret. As the secret changes, the file changes. That's the whole game.
So how does the application actually know the file changed? Well, that's where something called a file watcher comes in. There are libraries in almost every language, like fsnotify and Go, that let your application literally watch that mounted secret file for any changes. When a write event happens, that's your signal. You read the new password from the file and gracefully rotate your database connection pool. Just like that, your application goes from being static to being dynamic and totally responsive.
Now, if you want to get even fancier and honestly build a more robust system, you can use what's called the Sidecar pattern. The idea here is that a dedicated container, like the Vault agent, runs right alongside your application in the same pod. The Sidecar's only job is to handle all the messy details, authenticating with vaults, fetching secrets, keeping them renewed, and then it just writes them to a shared volume. Your application's only job is to read a simple file. All that complex logic is handled by the infrastructure, not your code.
And what's really cool about this is how simple it becomes for a developer. If you have a Sidecar injector set up in your cluster, you don't even have to manually configure this container. You just add a few simple annotations to your pod spec, and Kubernetes does the rest. It automatically injects the Sidecar, sets up the shared volume. It's an incredibly powerful pattern that separates your concerns beautifully.
But look, out of all the technical fixes we could talk about, this next one is hands down the most important. If your staging environment uses a static password that never, ever changes, then every single test you run is actually reinforcing the bug we've been talking about. You are not testing your app's ability to handle rotation. You are actively hiding the vulnerability.
Okay, let's just pause here for a second. Because everything we've just discussed about passwords, how they're loaded once, how they expire silently, how we need to dynamically reload them, all of that is about to apply to a completely different yet totally identical problem. And this right here is the central idea of this whole explainer. A database password that expires in 24 hours and a TLS certificate that expires in 90 days, from your application's point of view, they are the exact same thing. It's the same time bomb, just with a much longer fuse. One is a 24-hour outage waiting to happen, the other is a 90-day cliff. Both are just time-bound assertions of trust that, if they're not refreshed, are guaranteed to cause a failure.
So let's see how this actually plays out with TLS, because these failures are incredibly common in production, but you almost never see them in a typical simplified staging environment.
I bet you've seen this error 1,000 times. X509 certificate signed by unknown authority. Now what's funny is, this rarely means the server certificate is bad. It usually means that your client, your application's container, doesn't trust the authority that signed it. This happens all the time with minimal container images. They're often missing intermediate certificate authorities in their trust store. And hey, if you ever want to debug this live, you can just use OpenSSL-S client to see the exact certificate chain the server is presenting. You know, the same thing happens with MTLS too. If your client forgets to load its full chain, the server will reject you with the very same error. Trust is a two-way street.
So when you hit that X509 error in staging, the quickest, easiest fix is to just set insecure skip verify to true in your HTTP client. But this is not a fix. It's a security vulnerability waiting to happen. You're basically training your application that it's okay to function without validating trust at all. And that little flag, it doesn't know you're in staging. One simple config mistake, and that gets pushed to production, opening you up to man-in-the-middle attacks. It is a lie you tell your code, and it will come back to bite you.
So no, the answer is not to just turn off security. The correct approach is to build a staging environment that forces you to get TLS right from the very beginning.
And here are 3 concrete, actionable things you can do to make that happen. First, set up your own simple certificate authority for staging. Seriously, you can do this in 30 minutes with tools like Step CA, and it makes your staging trust model identical to production. Second, for every single external service your application calls, export a Prometheus metric that tracks TLS cert expiry days. Then alert when it drops below 30. You will never, ever be surprised by an expired certificate again. And finally, you have to explicitly test certificate rotation right in your CI pipeline. Your test can literally spin up a server, then halfway through swap its certificate on disk, and then verify that your client reloads it and keeps on working. This turns a potential production crisis into just another boring passing test.
Which brings us to the central thesis here, the one idea that really connects all of these failures and all of these fixes. It's something I like to call the staging lie.
You can use this checklist to go audit your own services, like today. How are you loading database credentials? Are you caching API keys in memory forever, which is just setting you up for a permanent 401 on authorized when they inevitably get rotated? Do you have insecure skip verify hiding anywhere in your code? And the big one, does your staging environment actually simulate time-based events like credential and certificate rotation?
And it all comes down to this. Your staging environment is not a playground. It is a model of production. And every single difference between that model and the real thing, whether it's a static password that never rotates or skipped TLS verification, every one of those gaps represents an entire category of bugs that your tests are completely blind to. Our job as engineers is to find those gaps and close them.
So we've gone through a ton of stuff here, from file watchers and sidecars to staging CAs and CI tests. But all of these patterns are really just designed to do one thing: make our systems more resilient by making them honest about the passage of time. The only question left is, which one of these ticking time bombs in your system are you going to defuse first?